And the first speaker is going to be Chris Burnt. I should explain that this has been organised by the UK NetworkPlus in Digitalised Surface Manufacturing, and I've got to give credit to Swarav for doing most of the work on this. And so we've got all week a series of very expert speakers speaking about thermal spray. Hopefully many of you were here yesterday and heard the two excellent talks we had, and we've got more today. And basically, I think I've, well, I ought to say that NetworkPlus is a group of 5 universities in the UK that have got together, Manchester, Sheffield, London South Bank, Queen's University Belfast, Cranfield, and we are successfully running now this network, and it very much parallels much of the work that Chris is doing in Australia, and Christian Morrow in Canada, and colleagues in India and Sweden, etc. So I think I'll pass straight over to Chris on this one. Swarav, is there anything else you want me to add?
Yeah, that's fine, Alan. I can just go through some of the other things. Sure. So thanks, Alan, for that warm welcome of the participants. So to the second day of the Thermal Spray Week, we had an exciting day yesterday, just to introduce to other colleagues, with talks from Professor Christian Morrow from Canada, presenting some aspects of diagnostics of thermal spray, and followed by very nice talk led by Professor Sanjay Sampath, giving us a history lessons of what we could learn in thermal spray area. So we covered the Western perspective yesterday. Today we bring the East and East Asian side to this Thermal Spray Week. So we start today's talk with Professor Chris Burnt in Australia, who is going to talk about architectural design of microstructures in this area. And we then have 2 exciting talks coming from Professor Rihan Ahmed and also from Professor Harpreet Singh, who are based in Dubai or Heriot-Watt University in the UK, and based at IIT Ropar in India. So those who are joining us fresh, I would just like to iterate on the fact that we have a dedicated issue on the Thermal Spray Week, which is basically going to be a historical collection of thermal spray manufacturing processes that is being edited by me with my colleagues, and is proposed to be published in Frontier. So all the keynotes that we are actually going to see in this Thermal Spray Week are going to be there. So it's a golden opportunity for all the thermal spray people, or people who wish to develop their career in this area, to come forward and actually cement your legacy in this golden collection through this issue, so that this issue or this particular activity that we have initiated will become a landmark in this area. So that was the initial thought that I wanted to pass on. And I would also like to say that just like we are doing this Thermal Spray Week, we have also decided to do and cover other coating processes through this EPSRC DSM initiative that includes, for example, physical vapor deposition or PVD, and as well as electrode deposition week that are going to become as some of the featured events of this DSM network in the time to come in the next few months. So please do register on the DSM website and be in touch with Dr. Pamela Sharma, who is the network coordinator. And now, keeping in the interest of time, I'm going to quickly introduce Professor Chris Burnt, who as such do not need any introduction, but I'm going to just say a few words. Professor Burnt is the Director of Surface Engineering for Advanced Materials, in short called as SEAM, which is an ARC or Australian Research Council funded center based in Australia, and parallels to the DSM, which we have here in the UK, or Green SEAM based in Canada. He has been involved in teaching and research within the materials engineering and mechanical engineering disciplines for well over 45 years. He has taken on leadership roles within professional societies, including the presidency of ASM International and the Australian Ceramic Society. He has impacted many thousands of undergraduates, including myself as an early career researcher, and many more postgraduate PhDs and lecturers that have started their career newly. He's especially proud of his students and postdocs, which he has been very vocal about, who have achieved professional prominence and have made good name for themselves. And he acknowledges their positive impact on his own career and professional life as well. So with that very brief introduction, I would like to hand over the floor to Professor Chris Burnt and would look forward to see what he has to share with us today. Thank you very much, Chris.
Thank you, Sarav. So I'm trying to share my screen and I'm going to ask for some verbal feedback when you can see my presentation.
Yeah, perfect, Chris. Please go ahead.
With the
plume.
With the pointer, I'm trying to show. Oh, there we go. Great. So, are we ready?
Yes, please, Chris.
Well, first of all, thermal spray week. Well, actually, thermal spray has been around for probably 100 years. So, I think that we need to remember that although about thermal spray for 3 wonderful days, thermal spray has been around for a long, long time and has a very long, long positive future. So what you see in front of you is a thermal spray plume, and into this plume, we have a lot of interesting things happening, and I'm sure that Professors Moreau and Sampath and many others have described these features. I'm just going to take a slightly different impact because I'll be talking about the architectural design. Now, this is in collaboration with many universities, RMIT Melbourne University, University of South Australia, IIT Madras, IIT Ropar, and of course, Stony Brook. And this is in collaboration with many people, and I'm just pointing out the people who are within the group now at Swinburne. It is also important for me to respectfully acknowledge the Wurundjeri people and their elders in past who are the traditional owners of the land on which Swinburne's Australian campuses are located in Melbourne's east and outer east. Before I get too far, I think that we should recognise that the last 2 years have been tough. They've been very tough around the world, and all of our colleagues, the thermal spray people, the PVDers, the engineers, the scientists, everyone has really had a tough time. So to the healthcare staff and essential service personnel, they've demonstrated their commitment and self-sacrifice. They are inspirational. We're all strong together. Thank you. These people are our heroes. Thank you very much. So whenever I give a talk, I always have a picture like this in the back of my mind because these are the ultimate customer for the thermal spray technologies, for the coatings and the PVDs and other coating technologies that the DSM network works with. This is but one small shop, which during the last 2 years has expanded 4 times this size because there's a huge market for these actuators. These are hydraulic actuators that go around the building, thousands of them, and are just for one specific industry called the coal industry. Or for Caterpillar trucks, these huge actuators are being pulled apart and refurbished within this workshop and the companion workshop, which is next door. So I always have this in the back of my mind: production, manufacturability, and cost. So whenever we talk about technologies to industry, these are the characteristics on the left-hand side of this table that people normally address. And for thermal spray, we can put down some numbers or some phrases about the attributes or otherwise of thermal spray coatings. And I'll be talking about some of these because eventually we compare thermal spray with CVD, physical vapor deposition, hard facing, and now additive manufacturing version 1, version 2, version infinity. So within this envelope, I always keep this in mind. This is not saying that these are necessarily good or bad, but these are just features that we need to keep in mind. So in the thermal spray process, as you learnt yesterday, we have a torch and we have a processing envelope in front of this torch. And this processing envelope is actually a combination of 3 overlapping PDFs, a probability, distribution function. So we've got temperature versus distance with respect to the particle size. We have velocity versus distance with respect to particle size. And then we've got the particle flux, which is being measured here. The particle flux versus distance with respect to particle size. So these three overlapping PDFs, probability distribution functions, is the deep science and the mathematics that we are hoping to control. And as I know this is a little bit of repetition, but I'm going to be talking about the final product here. I'm going to be talking about the coating, and the architecture of this coating depends on the inputs. The outputs depend on the inputs. The probability distribution function of powder injection, the PDF of in-flight phenomena, and the PDF of the splats which are being formed. And this has all got to do with the feedstock quality, the spray parameters, and the surface prep. So I'm just going to consider this as a process zone. And the process zone can be formed by either electrical energy, as in this case, or it can be formed by chemical energy, as for a flame spray and high velocity oxygen fuel. So I keep on talking about the architecture. So here is an example of the architecture of a very simple bronze coating, copper aluminium, on a grip blasted substrate. And we have all of these artifacts. We have splats, embedded grit, we've got cracks, we've got unmelted particles, we've got pores. So are these, this is the question, are these microstructural artifacts, are these a nuisance? And a metallurgist would probably say yes, because they're not very clean. Or can we somehow use these artifacts and use these features and give value to the customer? Can these microstructural artifacts be considered as attributes? So they could all be called numbers. They could all be, this is called a taxonomic definition. We can classify them as vertical cracks, interlaminar pores, splats, partially melted particles, unmelted particles, cracks in this direction or cracks in that direction, embedded grit. So the taxonomy of these coatings is not really understood or studied in great detail, but this is what we're missing out on. If we can look at these architectural features in 3 dimensions, if we can look at these architectural features, give them a number, and then somehow use them, then there are certain functional attributes which are highly desirable. And I'll talk about some of these via examples. So here's an example, very old, 1992, from University of Dortmund by Professor H.D. Steffens, one of the early workers. His thesis came out, decades ago, 50 years ago, 70 years ago. But what he was able to do with his group was get the chrome nickel fibers that you can see and get them embedded within a nickel chrome aluminium silicon matrix to get a composite with special functional properties: stiffness, dimensional stability, heat distortion, resistance to heat distortion, dielectric properties, etc. So the way that I am considering thermal spray coatings in these architectural features is that we have a Swiss Army knife. So we have this Swiss Army knife that we can use for surface engineering, and we can deposit composite coatings and freestanding components. Here's another relatively old example. This is not new, but it's the spin on how to use these features. So 20 years ago, we have the solid oxide fuel cells, again, in Germany from Professor Haney and others. I should also mention Professor Heberlein, did quite a lot of work in this area. And here we have quite a complex structure of a perovskite cathode, where porosity was desirable, an intrastabilized zirconia electrolyte where density was desirable, and a functionally graded nickel intrastabilized anode where the porosity and density varied in the thickness. So all of these architectural features, some people would say microstructural defects, but I'm saying architectural features are now being used to advantage. So this is but one example. And there are many things, many materials that can be used for this perovskite layer, and there have been books written about this specific topic alone. So here's some more recent work, the last few years. Now, this is a bioceramic coating, both produced at Swinburne. There's the traditional gold standard of hydroxyapatite, where we have the calcium phosphate, which has been sprayed on the roughened titanium, Ti64, titanium 6, vanadium 4 aluminium. And now here's the new material, Bagdadite, calcium, zirconium silicate. And you can see these architectural features, which all of these now have an attribute. They are highly desirable features within this very special coating that you could be wearing one day, or maybe your parents or grandparents are wearing one already. So the Bagdadite cracks, pores, splats, and unmelted particles. So these complex microstructures evolve from thermal spraying. We used to say spray and pray. So you spray it and you get these microstructural features. But now let's turn that around and look at the inverse statement. Can microstructures for specific functionalities be manufactured by taking into account these artifacts? So in other words, these artifacts, these architectural features are now highly desirable, and rather than spraying and guessing that we get them, how do we look at the inverse technological science and say we want to plan for cracks within a certain part of the coating at a certain density and a certain orientation, or pores of a certain size and morphology within a certain part of the coating. And by the way, this is where I think that the DSM network and that philosophy of carrying out experiments behind a computer can be very helpful. So I want to talk about antimicrobial coatings a little bit more because they are in fact beautiful. And we can look at the desirable properties of a coating on an orthopedic stem. Wear resistance of bacterial side coating, compatibility, killing bugs, killing microbes, anti-adhesive coating to repel pathogens. And this work was done under the Innovative Bioengineering Centre. So here's some strategies that a thermal sprayer would think about. How do we design the spray? How do we design the control, the temperature, the velocity, the particle size distribution, so that the surface roughness repels bacteria? How do we control surface roughness? How do we control the standoff distance and the thermal spray parameters so that we have porosity, so that we can have a biocide penetrating in 3 dimensions throughout the thickness of the coating? Or how do we control the degree of melting? How do we control the degree of melting so that we do get asperities, or we add a second phase so that we get contact killing of pathogens? So again, this is the inverse problem. As a thermal sprayer, these are challenges which are, well, they are very worthwhile to attack. So here's another example of a coating looking from the surface. And this is strontium hydrostomate garnite used for an orthopedic implant, not used yet. Now, this material is very interesting because it has antimicrobial properties. This coating, because of the zinc and the silicate, can kill bugs. So it's highly desirable. The hydroxyapatite, the gold standard, doesn't do that, whereas these new coatings do. And you can see the degree of melting. You start counting splats. You can see porosity is. You can see these little satellites or fine particles. And this is where the taxonomy, remember I keep on talking about particle size distributions. This is where measurement of what is happening at the substrate can give you hard numerical data on how you can control the power, the voltage and the current, standoff distance, all those parameters, how you can control that so you get a different character. Another example is high entropy alloys in collaboration with the Indian Institute of Technology in Madras. We start off with the powder, which we make in the lab, 5 elements all mixed together, approximately the same molar content. We spray a coating in the lab. We look at the cross section and wow, look at this chemistry. This has got a lot of phases in it. You can just tell by looking at it. Very complex. So a PhD student or two, Amy and Ashok, they start getting behind the microscope and they identify all of these phases. And colleagues in Madras, in Chennai, the black phase is alumina, which is good if you want a TGO, thermally grown oxide. We've got a grey phase, a white phase, and another white phase. So now, by carrying out the hardcore science, we're able to identify how this architecture can be described. We are actually putting numbers behind the percentages of these phases and where they're located within the 3 dimensions. Now, these coatings for high entropy alloys are intended to be competitive with bond coats, with the conventional nitrile used in the aerospace industry and the turbine industry. And it is only by carrying out this very intense and detailed microscopy and putting numbers behind the architecture. I'm not saying defects anymore. I'm saying architecture, behind all of these architectures and understanding the chemistry that we're getting the numbers to make good decisions. So again, I refer you to Amy and the paper that appeared a few years back. You've already seen this. I just showed you this. And I'm reminding you about a former figure, because all that we're doing now is we're trying to understand this particle distribution with respect to the temperature and the particle size. So let's look at a small particle. A small particle, which is in this part of the flame, will be mostly oxidized. But a big particle, number 9 here, a big particle within this part of the flame will not have as much oxidation. Now we can look at the inverse argument, going to figure number 7, sub-figure number 7. The big particle at a high temperature, right, which would be through the sweet spot, right? In cricket terms, this would be, you'd be hitting a 6, right, in cricket terms, or a 4. Sorry to remind all of my Indian colleagues about the cricket. But here we have the sweet spot, and you will get oxidation of the big splats, of the big particles, some oxidation. Whereas the smaller particles, this is not drawn to scale, but the smaller particles will be completely oxidized. So we can go through the complete logic map for these 9 different regions and start correlating to how these particles may have gone through, what part of the flame they may have transitioned in order to get to this state. So now we're correlating 2 of the PDFs. of the probability distribution functions. Now, let's get back to this diagram. We often compare this technology. Remember, it's been around for more than a week. Remember that we often compare it with competitive technologies. So I know there is some PVDs. So what have we learned from PVD? We've learnt many things. The Thornton diagram, very famous. And what it does, it allows us to relate generalized temperature with normalized energy and thickness, and we start looking at the PVD microstructural architecture. So you're able to predict columnar with equiaxed. This is what thermal spray needs, in my opinion. There is no such equivalent map that I know of, and if there is one, please bring it to my attention, that systematically gives such a summary of how the prime variables influence the microstructure. Now, there are many reasons why, and that is because there are so many features within the architecture. Remember the 13 that I referred to before? There are so many features that you need to analyse. So here's another way of looking at structures. Let me go back. So the PVD structure is desirable for many applications. So can thermal spray mimic the PVD structure? So liquid thermal spray is a potential technique. So in liquid thermal spray, we put a solution, a liquid, into a pump, we feed it into a torch, and we can either get a powder or we can get a coating on a substrate. What is happening within the torch is that we have particles travelling along and forming nanoclusters. It is important to note that liquid thermal spray includes suspension plasma spray and solution precursor plasma spray. And I'd refer you to the manuscripts by Dr. Karthikeyan. More recent work in the last decade at Swinburne looked at adding iron and cobalt and using those solutions as a metal alkoxide, feed that into a torch and look at the splats which are formed. Look at the architectural features. Why these materials? Because these are antimicrobial. And a companion study with our biology colleagues looked at microbe survivability with regards to the splat features. And Dr. Nope was able to demonstrate that solution precursor plasma spray technique could produce these cobalt ferrite splats satisfactorily, and he investigated the microbial properties. So we come up with a model which has been used by many people. This is a model, I emphasise. Not all aspects of it have been proven to be true or correct. But there are 3 steps, A, B, and C, where the liquid droplet forms solid phase of precursor condensates. We may get dense particles formed, and we may get aggregates, large particles, or agglomerates. So liquid thermal spray has now advanced even further. So in the more recent past, here are some examples. So on the far right, you see a conventional atmospheric plasma sprayed hydrostabilized zirconia coating, a conventional coating on a conventional bond coat on a superalloy. And now what we have is the same substrate, the same bond coat. We have an interlayer of a conventional coating, and now we have the solution precursor plasma sprayed yttrium aluminum garnet coating. with microstructural features of vertical cracks and layered pores. The vertical cracks mimic the columnar structure of a PVD coating. But this has been produced under atmospheric conditions. And the layered porosity is occurring in bands and has been proven to be a very effective impedance to thermal conduction. So it makes a good thermal barrier coating, for example. And Maury Girl at Storrs in University of Connecticut at Storrs has published in this area relatively recently. And others have also done this. Let me first of all read you the summary from the manuscript from these colleagues, from these gentlemen. Offers significant advantages: generation of nanostructured coatings, control of coating chemistry, and interesting microstructural features, which I will now focus on. So these artifacts from the liquid thermal spray, you got the vertical cracks in the past porosity bands that you just saw in the previous slide from Maury Gill. And then we've got porosity of various density. I can actually see a band here. This has not been quantified with regards to whether the distribution is even or not, but it's there. And then you've got the intercolumnar spacing, feathery, and columnar. This is a liquid thermal sprayed coating. Extremely interesting because it's been produced under ambient conditions. So let me remind you as I go into the last few slides. This is actually what is happening during plasma spray. We have the flame and we've got particles being injected into the flame. This is a real image. This is not a model. This is a real image. Some of the particles go into the flame here. Some of them see the edge of the flame. That's the cold ones. Some of them don't see the flame at all. So I also keep this image in mind many, many times because this is actually what is happening during the process. So in cold spray, this is the last part of the talk, Sarav, then I'll be closing down shortly. Cold spray is also used significantly now, and that has a relatively short history of a decade or so. As received, one component, machined, prepared for cold spray, build up with cold spray, finished machined, reinserted into the component. And there are many other examples. Just dial up Centerline in your search engine, and you see many other examples where cold spray has proven to be of economic advantage. Another technique which I'd like to talk about would be selective laser melting, because that is also a competitive technology. So in cross-section, here's a cold sprayed coating which has been heat treated by some technique called B by the authors of this manuscript. Selective laser melting is quite different. And what you see is the bands of the weld material, and you see the cross-section of it that goes back in 3 dimensions. This structure is more 3-dimensional because you've got individual splats. These microstructures are similar in 2 dimensions, but in 3 dimensions are very different. And I'll put down this curious comment about whether these are analogous or mimicking microstructures, because that is the intent of my talk. Can thermal spray, by understanding the architecture and the control parameters, mimic a process which is already working? So what do we know? I'm closing down now, Sarav, very shortly. We know a lot about technology. But the science is still there to investigate. We're all explorers. Thermal spray is a vast array of technologies. Design the microstructure to suit the application rather than just living up with what you get. You need to hit the target. This is all about processing conditions that can be controlled. And DSM network and modeling, these digital twins are not only important, but they are essential so that we can understand, so we can close the loop, so we can actually understand what we're doing. Last few slides, I do find it polite and courteous to acknowledge my funding source, the Australian Research Council. They are supporting SEAM. They're supporting a collaborative of 77 people, the majority of whom are early career researchers. I'd like to acknowledge that this talk rests on the shoulders of many people who have passed away, and there are many more, but these are ones that I know personally. And as Sarav introduced me, let us all encourage the future generations. And these are just a small subset of the people of the thermal spray group at Swinburne. Last two slides. We do create. Thermal sprays also create, as you can see here. Thermal sprays create, so when you go to the Sistine Chapel, keep this in mind. Thermal spray involves the right material, the right substrate, the right process, the right finish, and of course the right application. Very last slide. So we have a vision. We are all explorers. I've explained that thermal spray is a Swiss Army knife with a toolkit, various torches on this toolkit. We have microstructural artifacts, the architecture. This is a palette, just like a painter painting the Sistine Chapel. This is a palette which we must take advantage of to get the best functionality. We need to understand these control loops about the three probability distribution functions so that we hit the target, because these are essential building blocks for applications such as a knee here. Sarav, this is not the end. Thank you very much.
Thank you so very much, Chris. That was splendid. I mean, I can go on seeing it for hours. I mean, such a lovely architecture shown, which was very eye-opener to me, of course. I have myself a couple of questions, but I'll first maybe take few from colleagues who have been asking this in the chat box. So there's one question, Chris, from Francisco, which says, what are, in your opinion, the main roadblocks for the commercialization of liquid feedstock thermal spray?
Well, where do I start? The roadblock is that we need to have examples from industry which indicate success, because industry is very conservative. And this is exactly how cold spray became very popular, because the US government set up an activity which incorporated GM, Ford, Sandia National Lab and others. And over a period of 5 intense years, they came up with several applications that were successful for cold spray. And then a bunch of people saw applications within the military. So that is the major roadblock. They work, right? If you refer to the papers by Maury Girl, which I'm showing now, here's he and others in Sweden have shown very good data, but it's the conservatism of industry, as they should be, right? You never want an engineer to put something in which they're not happy with, but we need some examples where they work 110%. Hopefully that answers your question.
Thank you, Chris. I mean, if there will be any further follow-on questions, we can route them through email, through DSM network to you. I have two questions, Chris. I have been in the lab. I have seen how difficult each of these type of snapshots that you are showing it here takes, because you have to prepare your material sample, you have to do surface preparation, then you have to go and book the scanning electron microscope and then do further analysis. And times you can get what you wanted to get, and sometimes you don't get in terms of architecture. So my question is, how do you manage this kind of shared resources? Were they right away available when you wanted it, or you had to wait? Or is there a way around to do it in a quicker time frame if you would like to traverse the journey from producing a coating and then be able to see its microstructure by significantly squeezing the time window that goes in first spraying and then observing its microstructure?
For what I'm about to say, the DSM network, right? That's what we need. Organisations such as the DSM network, such as Green Seam, such as CTSR at Stony Brook, and of course Seam, right? But I've put others before me because that's just professional courtesy. We need these collaboratives to give examples and hit a 6 in cricket terms, right? I hate to use the word low-hanging fruit, but because the really interesting stuff is the high-hanging fruit. From a science perspective, the real interesting science is something which people find impossible to do. But the bureaucratic, administrative, low-hanging fruit really helps. And this is the compromise that all of those centres that I've talked about live with every day. It needs to be industry-driven, in my opinion, because industry ultimately pays the bills through taxes, and industry is a major audience for ECRs, for emerging and mid-career engineers and researchers. So it's the pooling of resources. That's a short answer, Sarab. Pooling of resources, and I will again go back to the DSM network, not because I'm speaking to the DSM network, but because I believe in it.
Sure. I mean, that's the intent, Chris, of course. One more question, Chris. I'm going to imbibe a term, because we talked about this architecture or microstructure of coatings. There is a term which is popularly used in the context of nature inspiration, referring to hierarchical structures. How flexible is thermal spray to basically manipulate the microstructure to obtain hierarchical structures, which are particularly used for biofunctional surfaces per se?
So I'm showing this chaotic microstructure now. So look at it this way: cancellous bone, cortical bone, osteons, right? There's a biological structure. We can mimic cancellous bone with porosity, right? Because that's the marrow, the bone marrow. We can mimic the cortical bone in terms of density. Hence, it comes no surprise that hydroxyapatite, if I can get back to it, hydroxyapatite, here we go, that is mimicking natural bone. But that's a chemistry. What I would like to propose or challenge, this is the challenge, the scientific challenge: can we do more than just mimic the chemistry? Can we mimic the growth rings of cortical bone, as an example? Now, this is where I could show the this slide. Can you see my pointer? There's some growth rings.
Yeah.
Right? So there's the growth rings, and in between, I don't know what this is, but we need to speak to a biologist. But what I'm saying is that these architectural features can, and I'll get back to the cartoon, the architectural features can be taken advantage of, but the critical path is to measure them and carry out what I call the taxonomy of these architectural features, and I keep on referring to PDFs, probability distribution functions. So whenever you open an Adobe document now, I want you to think about a probability distribution function.
Sure.
Right? So because that is what we, as surface engineers and material scientists, etc., would find very interesting to classify. Okay, Sarath?
Yeah, thank you, Chris. Chris, one more question I have. Sorry for these questions, but you are such a resource of knowledge that I would like to take the opportunity to address some of the burning questions that people have had for many years, and the answers to that are still puzzled. One question, Chris, that has come out, because coming from a subtractive precision manufacturing community I always had, is can you control residual stress during spray, or is it something that is beyond our control?
Residual stress has been a subject of books for thermal spray, and has been a subject of many issues of JTST, General Thermal Spray Technology. And it's been published in thin solid films and, of course, SCT, Surface Coatings and Technology. The word that I would hang on would be control, right? If you're using control, I'm becoming very pedantic now, please forgive me. If you're using the word control in the engineering sense, yes, because we've got preheating, post-heating, standoff distance, the substrate geometry. We can control, in the engineering sense, residual stress. And that will vary from component to component, from torch to torch, even if the torch is the same torch. And that was verified in the Booth equivalency exercise by Walter Riggs, who was on that very last slide. He passed away a little while ago. And he worked for GE when he did the Booth equivalency test, which was published about 20 years ago. But now, talk about control in the scientific sense. The answer is, we are all explorers.
I see.
Right? I find it very difficult to go out on a limb and talk about control in the scientific sense. The modelers, though, right, DSM, the modelers can put those features that control residual stress, coefficients of thermal expansion, cooling rates, thermal conductivity from the substrate, surface roughness, a specific surface area. They can put that into their models and numerically quantify residual stress. And I would refer you to a manuscript by Professor Rihan Ahmed, who is the next speaker, who wrote a wonderful review paper on that topic, specifically on that topic. So there's been a lot of modelling, but the measurement, that is the difficulty. The measurement, because you need a highly sophisticated source, a beam, such as what Professor Withers has, and is an expert at, within the Rolls-Royce Activity Centre Institute. And that equipment is very tough to get onto. Okay, Sarath?
Yes, thank you so much, Chris. Actually, we had one of the webinars, just for the wider benefit of the audience, from Professor Faisal, based at Robert Gordon, who actually explicitly covered some aspects of residual stresses in coatings, which is a delight to watch on YouTube channel of DSM. So I think that concludes the questions, Chris, from my end. And I would like to once again thank you so very much for this wonderful talk and taking us very close, almost to the spray gun, what we have deposited on the eyes of microscope. It was splendid, as you can see from the chat box, colleagues have already mentioned. And we really thank you so very much for this.
So my last word is, thermal spray is more than 3 days.
We wish, Chris, we could do it for over the year or many years, and it will keep on doing that way, in fact. And that's why we actually have come up with this journal, which is going to create that spirit in the long terms.
I shall now stop sharing, and since it is late in the evening, I need to go somewhere else. Thank you very much. Goodbye.
Thank you, Chris. Thanks again. So after Chris, we would now like to welcome our next speaker, Dr. Rihan Ahmed, who actually, as Chris just mentioned, has written a very wonderful review paper on modeling and tribological aspects of spray coatings. Rihan, are you able to hear me? Yeah.
Saurav, yes, I can hear you. Can you hear me?
Good to see you. Yes, I can hear you. So Rihan basically is an expert in the tribology of surface coatings and leads multidisciplinary research in the area of mechanics, materials, and manufacturing. He's based both in Dubai and in the UK because of its association with Heriot-Watt University, my alma mater. So it's always a delight to see that logo, Rihan. In this area of research of tribology, Rihan has successfully secured more than 17 competitive research grants with well over 2.2 million pounds of income from both industries and research councils. He recently secured 2 patents in the area of biomedical coatings and solid oxide fuel cells, and he has published more than 100 scientific papers. Currently, Dr. Rihan is the Associate Director of Research in the School of Engineering in Physical Sciences at Heriot-Watt. His previous appointments were at the University of Cambridge, Al Faisal University, and Brunel University. Is Associate Editor for IET Journal of Engineering. He serves on editorial boards of several journals, including Journal of Thermal Spray Technology and Advances in Mechanical Engineering, and regularly reviews articles related to coatings for many various journals. He was also the guest editor for 2 special issues of JTST on nanocomposite coatings and biomaterials and thermal spray processes in applications. And his accolades are many more because I have seen and never got the opportunity to tell him personally, because I've heard about him a lot of positive things and his peers holds him in very high respect and regard for his scientific rigor in research. So with that brief introduction, Rihan, I would like to welcome you and look forward to listening to your talk.
Thanks very much, Saurav. Really appreciate that. So I'm just going to start sharing my screen, and I hope that if you can just please confirm when you're able to see it. Saurav, are you able to?
Very good, very good to go. Yeah.
Okay. Thank you very much. So I just need to just close some of these things. So that is not obstructed. My apologies. Sorry, just trying to close all the that should do it. Right. Okay. So once again, thanks very much, Saurav, for the introduction, and I am grateful to the team at the EPSRC Digitalised Surface Manufacturing Network for inviting me to deliver this webinar. In this webinar, I will be talking about the modeling and tribological design considerations of spray coatings. And I would also like to say a warm welcome to all the attendees in this webinar. So this webinar links a little bit with the discussion Chris was having in terms of residual stress, and we're talking a little bit more about tribology. So as we move towards digitalized manufacturing, there is a greater demand to reduce the coating development costs when optimizing design for current and mobile markets. And modeling in this respect plays an important role as it not only integrates with the manufacturing tools, but also provides an understanding of the high-speed lamellar interactions, which are difficult to otherwise visualize using the experimental techniques. And some of the examples we'll be looking at today are linked to tribology. And tribology is a multidisciplinary area of research, and it deals with the science and engineering of interacting surfaces and relative motion. So it touches a number of aspects of our society, from the design of artificial human joints and computer hard disks to the movement of glaciers and interaction of space debris with the solar panels of the space station. So almost 23% of the world's energy consumption originates from tribological contexts. Now, this is not as bad as it sounds, as life as we know it will not exist without the natural phenomena of friction and wear. For example, we will not be able to walk without friction or manufacture components without the removal of material, which is also a tribological phenomenon. So in terms of the structure of my presentation, the webinar can be broadly classified in two sections. And in the first section, we will look at the science and engineering of the generation, measurement, modeling of residual stress and thermal spray coatings. And in the second section, we will look at the science and engineering of interacting surfaces in rolling context and also sliding context. So, and we will do this with a view to understand the structure property relationship, generate wear models and maps. And finally, we'll look at some of the design criteria and future sort of directions of this research. So I'll start off with the example of hydroxyapatite coating for orthopedic implants. And thermal spray technology is currently the most viable method to deposit hydroxyapatite coatings for biomedical implants. And the structure property relationships of biomaterials such as hydroxyapatite play an important role in the performance of artificial implants due to mechanical loading, osteointegration with the surrounding environment, and a good quality hydroxyapatite coating provides longevity of the implant, and it reduces the rejection rates of implants, and therefore it improves the quality of the patient life. There are a number of attributes which make up the desired structure and properties of hydroxyapatite coatings. And some of these include correct level of porosity, calcium to phosphorus ratio, the ratio of the crystalline to amorphous phase, the adhesive strength of the hydroxyapatite coating, etc., etc. And although the US Food and Drug Administration do not require a residual stress profile and thermally sprayed coatings for the approval process, through thickness residual stress profile plays an important role dictating the desirable characteristics in the implant. So the through thickness residual stress profile in these coatings changes during the life of the implant. So it's like a living thing, you can say, and it changes due to the mechanical loading. It changes due to the interaction with the biological environment in the body, and any post-treatment which has been applied to the coating. And in the example shown for the hip implant here, the femoral stem is coated with hydroxyapatite coating, and the implant is subjected to a compressive stress and a tensile stress throughout its life, which can lead to failure amongst other factors such as the biointegration. So this slide shows the surface morphology of hydroxyapatite coatings in the aspirate, heat-treated, and coating subjected to simulated body fluid environment. So the SPF, or the simulated body fluid environment, is used to ascertain coating response in the bioenvironment, and significant changes can be observed on the surface of these coatings in these conditions. And these changes also influence the residual stress profile in these coatings as shown in the next slide. So before I actually dive into that, I just want to classify how do we actually experimentally measure residual stress. And experimental techniques adopted to measure residual stress can be broadly classified into three main categories. The first ones are non-destructive, and these are the techniques such as the neutron diffraction, the synchrotrons, and the X-ray diffractions. And Raman spectroscopy also come in this category. Then we have the semi-destructive techniques such as the hole drilling, diametral compression, and layer removal or modified layer removal. And then finally, we have the destructive techniques such as sectioning and contouring. And there are some in situ techniques such as the curvature method in which you can actually get an idea of the residual stress profile of the coating. So the slide shown here shows the through thickness microstrain measurement in the hydroxyapatite coatings in the air sprayed, heat treated, and subjected to simulated body fluid conditions. And the term through thickness here is important because you need to understand the profile of residual stress near the surface at the coating substrate interface and within the substrate itself. And this particular measurement shows the analysis based on two different crystallographic planes of 030 and 022. The measured strain is significantly different in these two planes, and these differences highlight the importance of measuring residual stress across different orientation and use averaging or Rietveld refinement or some other techniques to comprehend the overall residual stress profile in these coatings. Once the multiple peak analysis is conducted, the average microstrain in these coatings can be analyzed to give an overview of the overall stress field, as shown in this slide. And now the slide also shows the technique, the changes in the through thickness residual strain profile caused after the heat treatment and subjected to simulated body fluid conditions. Further changes in the residual strain profile can be expected due to mechanical loading during the life of the implant. So in conclusion, what we can say is that the residual stress profile is dependent on the type of analysis or the type of neutron diffraction or non-destructive analysis, and changes due to post-treatment and bioactivity in these hydroxyapatite coatings. So moving on, I just wanted to mention that some of our later work led to a US and a European patent, which integrates not just thermal spray, but also other coating techniques such as the physical vapor deposition and the chemical vapor deposition to actually improve the quality of the hydroxyapatite coatings for orthopedic implants. So the residual stress profile in thermal spray coatings is also dependent on the measurement technique. And this slide provides a comparison of residual stress measured by the non-destructive neutron diffraction and the semi-destructive hole drilling technique. The measurement is made in a bilayer system. So we have a 300 micron thick tungsten carbide with 10% nickel chrome boron silicon matrix, and then 100 micron thick tungsten carbide with 40% nickel chrome matrix. And then the substrate is a 440C stainless steel. And the difference between the two results, between the neutron and the hole drilling, lies in the type of residual stress being measured in these coatings. So care profile need to be considerate of the type of measurement technique when we are basically measuring residual stress or deciding which technique to apply. So this slide provides the comparison of the same coating, which I showed in my last slide of the bilayer system. And it shows the changes in the residual stress profile through thickness in the coating and the substrate system after it has been heat treated at 1200 degrees Celsius. And the changes in this particular case are linked to the sintering of the carbide as shown in the Astm, and also the formation of a diffusion layer near the coating substrate interface. And this slide gives another example of the changes in residual stress profile caused by the differences in the deposition techniques of air plasma spray and high velocity oxy-fuel spray. The measurement was done using neutron diffraction method in this particular case. And as these coatings are brittle, aluminum oxide is quite brittle material, and have a complex microstructure, it is not always possible to get a reliable measurement using the destructive or semi-destructive techniques such as the hole drilling, where the coating can crack. So this is shown by the insert here, where the residual stress profile measured by the hole drilling technique becomes unreliable. So care need to be taken when selecting measurement technique in thermal spray coatings, as not all the techniques can be applied to all materials. This slide provides another example where the depth of residual stress measurement can be made specific to near surface measurement. And in this case, we use synchrotron technique. And this can be useful when interpreting changes in residual stress due to sliding wear or other near surface phenomena. So you have the residual stress values before the wear test and then after the wear test, basically. So measurements were done at two energy levels of 15 keV and 25 keV to change the depth of measurement using the synchrotron measurement. And although neutron diffraction is the gold standard of measurement for through thickness residual stress profiling, some of the near surface changes can be better captured by the synchrotron beam. So we have now established that the residual stress profile in thermal spray coating is dependent upon the type of stress measured and is influenced by the changes in coating process, measurement technique, changes due to the environment such as bioactivity or mechanical or the wear process. We can now categorize the mechanism of residual stress generation in thermal spray coatings as those caused by the peening effect, the quenching effect, and the differences in the coefficient of thermal expansion. So peening causes compressive residual stress, prominent in cold spray or high velocity oxy-fuel processes. And the video on the right shows a cold spray impact where the black contours indicate the compressive residual stress caused due to the peening effect. Quenching stress is caused due to the contraction of the impacted particle or lamella, and when its contraction is constrained by the underlying material or lamella. So quenching stresses are always tensile due to the restricted contraction. And in this slide, you can see that the temperature cools from high temperature to low temperature. The quenching stresses will eventually develop in the splat, and then as the coating builds up, basically. So thermal stresses, on the other hand, are caused due to the difference in the coefficient of thermal expansion of the coating and substrate materials, and these stresses can be tensile or compressive depending upon the mismatch of the coefficient of thermal expansion. So for example, a compressive residual stress will be formed in the coating and tensile in the substrate if the coefficient of thermal expansion of the substrate is greater than that of the coating. Other considerations when we are looking at the generation of residual stress are the cracks and phase transformations and post-treatment which has been applied to the coating. So all of these factors influence the overall residual stress profile. So having looked at the measurement and the generation of residual stress, we can now draw our attention to its modeling. And there are 4 numerical modeling techniques which can be adopted to evaluate residual stress in spray coatings. And these are Lagrangian, Eulerian, smooth particle hydrodynamics, and molecular dynamics. So in the Lagrangian analysis, the mesh deforms to mimic the deformation of the material as shown in this slide. So here you had the original material or the original mesh, and as the mesh deforms, basically it accommodates the elastic and the plastic strain in the material. It can run into some stability issues. For example, here the aspect ratio of the elements have gone really bad, and that can lead to basically either incorrect results or the termination of the program. In the Eulerian analysis, the mesh is fixed and the material is allowed to flow in and out of the mesh as shown in this slide. So you have the original mesh, which is over here, and then the material basically just flows in and out of the mesh to accommodate the elastic plastic strain. The technique can be used to capture large deformations without stability issues or issues related with the aspect ratio of deforming mesh in the Lagrangian analysis. And it is also possible to actually combine both Lagrangian and Eulerian analysis, for example, where the splat can be modeled as a Eulerian part and substrate a Lagrangian in thermal spray coatings. Smooth particle hydrodynamics is another form of Lagrangian method in which the elements are discretized as particles to model material deformation. And this is achieved using a mass function or a smoothing function. Molecular dynamics is generally used in small-scale deformations, and molecular dynamic simulations can capture the interaction of atoms or molecules using the classical equations of motion. Now, grain boundaries, structural transformations, friction, and shock waves are some of the fields where molecular dynamics has been applied. And this slide shows the particle interaction of a 21.4 nanometer diameter particle of titanium at 3 different velocities of 350, 500, and 700 meters per second. In addition to these methods for modeling residual stress, analytical and mathematical modeling techniques can also be applied to model residual stress in thermal spray coatings. So how do we compare the techniques? So each numerical technique has its advantages and challenges when applied to understand the lamellar interactions and residual stress modeling. Lagrangian is the most common technique because of its accuracy. However, Eulerian has captured interest due to the capability of performing large deformations without numerical or programming errors. So the image to the right shows a comparison between Eulerian and Lagrangian model, and it can be seen that the Eulerian deformation is similar to the experimental observations. Smooth particle hydrodynamics has been successfully applied to model high strain rate deformations. However, challenges remain in acquiring the correct combination of material parameters and particle connectivity. So the image shows a back-to-back comparison of modeling using a pure Lagrangian, and a smooth particle hydrodynamic as the particle in the substrate, and then smooth particle hydrodynamic alone, or on its own kind of modeling. Coupled Eulerian Lagrangian provides a better balance between accuracy and large-scale deformations. In this technique, the Lagrangian is usually the substrate. However, in cold spray coatings, the substrate can also undergo large deformations, and there are chances of abnormal deformations in the Lagrangian mesh. Hence, CEL is better suited for thermal spraying rather than modeling of cold spray coatings. And I'm just going to show 2 examples of simulations performed using the Eulerian method. And on the left-hand side, cold spray is a cold process and requires only dynamic explicit simulation, and there are minimal thermal effects, and it requires mostly mechanical properties. On the right, on the other hand, plasma spray process is a hot process and material undergoes solidification. So therefore, it is crucial to include thermal properties as well as mechanical properties, which are both temperature dependent. And sometimes acquiring these right combination of properties is where the challenge lies. So if you are able to model the splat behavior and residual stress behavior, in certain instances, we can extract some additional information. For example, in cold spray, these models can help understand the influence of critical velocity on particle adhesion. Too low velocity can lead to particle rebound, and too high velocity can cause excessive jetting, leading to material loss. So in terms of the bonding mechanisms, there are two schools of thoughts which rely on either the adiabatic shear instability or the pressure waves causing the hydrodynamic plasticity when we're looking at the bonding mechanisms in cold spray coatings. So yes, we can model, but it's crucial to validate these models. Because models always give you some results, but how reliable and how accurate are these results? So although we saw single particle impact, we can also stack particles using the same methodologies as discussed earlier and have multiple particle impacts to obtain the residual stress profile for thick coatings. And the first work here compares the residual stress of a yttrium stabilized zirconia on stainless steel substrate. There's a fairly good relation between the two, except for the high tensile stress in the coating. And this could be due to the assumptions in the model, and also yttrium stabilized zirconia is prone to microcracking, which could have reduced the residual stress from the experiments conducted by Monte. The second example compares models between the experimental and the theoretical finite element, and the model is able to predict residual stress to a fair extent, and the experimental work here is obtained using the neutron diffraction technique. The third example uses the destructive contour method, which is, and then compares it with the analytical prediction with neutron diffraction. This work also seems to have fairly good correlation. Obviously, there are some outliers when compared to the analytical prediction, and also differences between the experimental methods due to the inherent differences in the experimental techniques. So this brings us to, where is this science heading? What's the future, or what are the future challenges in modeling residual stress in thermal spray coatings? So modeling cracks is still a challenge, and as we have seen, some of the materials can be subjected to cracks. And these cracks can alter the residual stress rate. And this needs a combination of conventional finite element method with techniques such as extended finite element method to be able to incorporate cracks. There could also be phase transformations during the solidification, or phase transformations related to high strain rate, which are not considered in these models. And these can influence the residual stress due to some extent. This may require some form of coupling with molecular dynamics or phase diagram soft phase. Multi-scale modeling becomes crucial to simulate residual stress in larger components, and this includes combination of different techniques at different scales to study residual stress. And this is the way forward as we move forward in the computational modeling of residual stress. So we have now looked at the modeling of residual stress, and we can now pay some attention to the second part of this webinar, which considers the topological applications and how these modeling techniques can be adopted to capture the wear process. And in the interest of time, I will only be looking at tungsten carbide cobalt coatings. So in the centered form, tungsten carbide cobalt provides a good combination of hardness, fracture toughness, elasticity, and strength when compared to other candidate materials such as silicon carbide, alumina, and silicates. And although the magnitude of these values are lower in sprayed coatings, they still provide a good combination of properties for topological applications in non-corrosive environment up to an operating temperature of about 500 degrees Celsius. For example, the Young's modulus of thermal spray coatings is roughly 1/3 of the sintered value. And similarly, fracture toughness ranges between 2 to 14, depending upon the coating process as well as the direction of fracture toughness measurements. The Astm images on the right show typical microstructure using conventional JP5000 and jet coat techniques, and also suspension high velocity oxyfuel in both aspirate and also heat treated conditions. So thermally sprayed tungsten carbide cobalt coatings are used in a variety of industrial applications to protect against abrasive wear, erosive wear, sliding wear, and fretting fatigue. And some of these applications include impeller shafts, aircraft flap tracks, conveyor screws, and as the science and engineering advances, there's a potential for new applications. Now, in the centered form, they are also used in a variety of other applications. So the wear performance of tungsten carbide cobalt in both centered or coated form is dependent on carbide size, cobalt content, amongst other microstructural and tribological considerations. So predicting the sliding wear performance of coatings requires us to understand the complex interdependencies of the wear mechanism. And before we embark on full-scale testing of coated components, the cost of development can be significantly reduced using the ASTM test procedures. And in sliding context, there are three important tests, which are either used independently or in combination to understand the wear mechanisms and predict the wear rate. So in ASTM G133 and G99, the normal load is applied to the ball or the pin, and the difference between them lies in the sliding direction, which is reciprocating in G133 and rotary in G99. Another configuration is the ASTM G77 block on ring test, as shown over here. Now, in all of these tests, we measure the wear volume using the wear scar and use the information about the normal load and the total sliding distance to evaluate the wear rate. And the post-test evaluations of these wear tracks can help us identify the wear mechanisms. And a number of factors are important here, as discussed in the next slide. So in terms of the tribological test conditions, test method and test parameters, such as the material of the counterbody, the load, the speed, direction of motion, and the environmental conditions, they all play an important role in the sliding wear process. And the selection of these parameters influence the contact pressure, the formation and removal of the tribofilm, and the entrapment of any wear debris, leading to three-body abrasion within the wear track. However, these are all dependent on what method you have used for the measurement of wear. And that's only half of the story, because the other half of the story lies with the selection of the coating process parameters, and the characteristics of the powder, and which all influence the structure property relationships. And the combination of the two halves of this diagram indicate the complexity and interdependency of the design parameters when we are designing coatings for sliding wear performance. Factors such as the elastic modulus, hardness, and fracture toughness of the coating, and the other materials such as the ball material or the pin material, along with the surface chemistry of the test couples influencing the tribofilm formation, plays an important role. So the failure modes of these coatings in sliding wear can be classified in 6 main categories. So the first one is the carbide pullout, where the carbides are just simply extracted, or they leave the matrix. Carbide fracture, which is shown as transgranular fracture in this particular case. Preferential wear of the matrix, leading to the exposure of the carbides, and the importance of the protective tribofilm, which not only depends upon the counterbody material, but also the tribological test conditions. And in most cases for these coatings, WO3 is the most dominant tribofilm which reduces both the wear rate and the friction. Now, repeated sliding can also lead to near surface and subsurface cracks, leading to coating delamination, as shown over here. And then the changes in the wear mechanism from two-body abrasion to three-body abrasion, which can be caused by the entrapment of the wear debris within the contact region. Similarly, for the counterbody, we have change in the contact area because the counterbody also wears, and there can also be some tribofilm formations and grooves on the counterbody material. Now, let's just talk about how we model the wear rate, because in the design process, we need to be able to understand what the wear rate will be based on the different design considerations. So in terms of the semi-empirical modeling of wear rate, there is no generic relationship between hardness and the wear rate. And we can extend this analysis to say, okay, ratio of the ball to coating hardness to wear rate, or the contact pressure to wear rate. None of them actually have any correlation. And this is because of the complexity of the sliding wear process in thermally sprayed tungsten carbide cobalt coatings. However, once we include all the factors such as the contact pressure, the coating hardness, the ball hardness, the fracture toughness of the coating, the elastic modulus of the coating, and the ball material, we begin to see some trends. However, the trend is still not well defined. And the problem lies in the way we define wear rate itself. See, the wear rate has a force term, which is the normal load over here. And this alludes the wear performance because the influence of a given load is geometry dependent. For example, a load of 25 Newton on a steel ball of 10 millimeter diameter is not the same as a load of 25 Newton on a tungsten carbide or a ceramic ball in terms of the contact pressure. Now, even for the same ball material, as the load changes, the contact pressure changes non-linearly. So hence, we can include the influence of geometry in the wear rate calculation by replacing the force term with the Hertzian contact pressure CP term. And once we do that, we begin to see the difference in the wear rates as shown in the next slide. So here I've replaced the load term with the contact pressure. And once we have replaced it, we can see the trend which can be applied to both conventional and nanocomposite and other HPF coatings. So you are beginning to see some sort of trend forming by these changes. And as can be seen in this figure, we can distinguish between the performance of HPF and plasma spray, and the axis or the x-axis of this figure, which is plotted on a log scale, shows the complex interdependencies of the factors influencing the sliding wear process. At higher temperatures, the story is completely different because at higher temperatures, the wear rate of tungsten carbide cobalt accelerates exponentially. And this is shown on the log scale because we couldn't fit the whole thing in one go. And two factors play an important role as the temperature increases from room temperature to about 650 degrees Celsius. The first factor is the temperature-dependent changes in the mechanical properties of the coatings. As the temperature increases, the elastic modulus and hardness decreases, whereas the fracture toughness is expected to increase. However, due to the microstructural phase changes leading to eta phases at higher temperatures, the toughness also decreases. The second factor, which is probably the more important factor, relates to the test conditions and the instability of the protective tribofilm. You see, WO3 or the tribofilm actually protects the coating and reduces friction and wear. And this figure shows an analysis of the variation in sliding wear properties or rates of air plasma spray, high velocity oxyfuel, and low pressure plasma spray coatings in the temperature range between 25 and 650 degrees Celsius for a range of tungsten carbide based coatings. So it's just not tungsten carbide 12 cobalt, but we have some other coating types which are also compared in this slide. And these tests are conducted in air and in argon environment. And the argon environment in particularly substantially increases the wear rate, shown by this one over here, as the absence of oxygen does not support the formation of the low friction and protective tribofilm under these high temperature conditions in argon environment. So that's a little bit about sliding contacts. We can move on to a slightly different type of contacts, which are the rolling contacts. And the main difference between the rolling contact and the sliding contact, that in pure sliding, the coefficient of friction is much higher and the maximum stress appears on the surface. Whereas in pure rolling contact, the maximum shear stress, or the stress driving the cracks for fatigue and delamination, is subsurface, as can be seen over here, this simulation as well. And rolling contact fatigue tests can be performed using a modified ASTM STP5048. And in this test configuration, the coated specimen, which is to be a cone or a ball, rotates against 3 planetary balls and until the specimen fails. And these tests are usually performed in lubricated conditions. Now, these tests give us 2 important pieces of information. The first one is that the rolling contact fatigue life in terms of number of stress cycles to failure. Remember, in sliding wear, we were calculating the wear rate. Here, we are calculating the number of stress cycles to failure. And secondly, the failure mode of the coating in rolling contacts using any sort of post-test evaluations. The other notable difference is that the friction coefficient in rolling contacts is generally an order of magnitude lower than in sliding contacts. So delamination being a dominant mode of failure in rolling contacts. In this mechanism, the cracks propagate subsurface. So you have this is a cross-section of the coating, so that's the surface. And then you have subsurface cracks, and these cracks appear at 2 different depths of 0.35A, which is the depth of the orthogonal shear stress, and 0.48A, which is the depth of the maximum shear stress. And in the SEM shown over here, you can see how the delaminated coating basically looks like, where A in this particular case represents the width or the half width of the contact between the 2 bodies. So the failure in rolling contacts can be classified apart from delamination into 3 other categories, such as abrasion, bulk failure, and spalling, as shown over in this slide. And the SEM observations here indicate the morphology of these failures. And if we fully understand these failure modes, it is possible to design coatings to stand 70 million stress cycles without failure, which is generally this industry's standard for bearings. And I will look at that in the next slide. So in order to map the failure of these coatings, we have to use non-dimensionalized maps, and I have normalized the contact pressure here with the yield strength of the substrate on the y-axis, and then I've normalized the coating thickness with the depth of the maximum shear stress. And once we do that, we can map out the different types of failures, and we can then try and design coatings where it is very likely that we are not going to have any failure, for example, as shown by these yellow areas. And then the blue and the red areas are the areas which really need to be avoided in the design process. The lubrication regime is shown as the secondary axis in this particular slide, where the full lubrication regime indicates that there is no asperity contact between the ball and the coating surface. So, having looked at the experiment evaluation and mathematical modeling of the wear rate or rolling contact fatigues in the previous slides, I'm just going to talk briefly about the numerical modeling of the wear process. The numerical models for the wear process are in their infancy at the moment. However, they can provide some useful prediction of the wear rate. And there are 2 approaches which can be adopted to model sliding wear and finite element method. The mesh deletion method, as shown here, is based on some sort of criteria where the mesh gets deleted once it's got to a certain failed criteria set in the software. And then the deleted mesh or the deleted part part of the material represents the wear volume. The second approach is called the node adjustment in the contact region approach. And in this particular case, what we have is basically originally some nodes are categorized in the contact region. And then as the wear process continues, these nodes shift downwards, given some sort of criteria or algorithm within the software to accommodate the volume of wear within the process. So where's the future? The future of wear modeling lies in modeling the coating material, including its microstructural phases. Because at the moment, what we do is we use coating as a single material without any consideration of its defects or secondary phases, which is not really an ideal. And this is what is shown in the in the first video here, where the material is modeled as a single material. We can, however, model the matrix and carbides as two separate phases. And the second video shows how the carbides in the microstructure can be included in the elastic plastic scratch model for composite alloys. So this is the one where we have modeled the matrix and the carbide separately, and the bright red regions, which will appear any minute now, hopefully, will actually indicate the carbides within the material. And this approach can be coupled with a wear rate numerical model to improve the accuracy of the sliding wear results. And the model can also integrate the residual stress profile during the wear process, as indicated earlier on. So we can couple all of these things together. So this concludes my presentation. So in conclusion, we can say that numerical modeling techniques can be adopted to model residual stress behavior of both thermal spray and cold spray coatings. It's possible to connect all these models and link structure property relationships and incorporate the role of residual stress in the coating development. And numerical modeling of sliding wear is an emerging area and can be further developed to facilitate the design process. And contact fatigue failure modes and mapping can be used to optimize the design process. So finally, I would like to thank my research team and collaborations, and I'm grateful for the support of the present and past research team members, research councils for funding, and the academic and industrial partners in this research. Thank you very much for listening, and I hope that you find it useful. I will pass the floor back to Saurav now, so I will stop sharing. Thank you very much.
Thank you so much, Rihan. That was splendid, well kept in time, and the information very well conveyed. As I was hoping that if there are questions from the audience side that I can say a few, but maybe Gustavo, we would like to begin.
Thank you for a very interesting presentation. It's very, very interesting the interconnections you were showing in terms of residual stresses and material properties. I wonder if there is any concrete example in which design of coating has actually been informed by models, because you said it that it can be done, but has this been actually done to produce a commercial coating?
Sorry, are you talking about actually developing a coating with a given stress profile?
Well, so the modeling, you show us several models, right? Different modeling options. And in many cases, these were related to prognosis, residual stresses, what is that you're gonna get, right? What is the life, what is the wear? So have those models actually has been employed for designing coatings rather than just for prognosis, you see?
Yeah, I fully understand. I think this is an area of research which is still undergoing, and I think it's a good question, because at the moment we are at the stage where we can couple different modeling techniques to predict residual stress, and then we are at the stage where we can then compare the residual stress with experimental techniques to make sure that we have some confidence in the in our stress evaluation. However, the question you asked is actually much bigger, because that asks about integrating this with the manufacturing process itself, which is, with the digitalization of the manufacturing process, artificial intelligence, neural networks into the, coating process parameters and everything else, the future probably is where what you're suggesting, where basically you can actually use or design the coatings at the development stage to at least try and have some idea of what the stress profile will look like. But we are not there at the moment. We are at the stage where, even now, where there is no in situ real technique of measuring residual stress at the moment. We have the curvature method, for example, but it doesn't tell the profile. And I think what I said in my earlier slide was, it's not measuring residual stress or strain in one location, it's the whole profile. And the in situ measurement, which we have at the moment, only gives just an average value of residual stress. So until and unless we get to the stage where we can connect the in situ development of residual stress, which is not going to come from an experimental technique, it's going to come from modeling, because currently there is no technique to measure in situ residual stress. The whole process is too fast, it's too hot, and even if you use the state-of-the-art neutron beams, it's just going to be too complex to measure. But the future definitely lies in that direction. How long will it take to get there? I have no idea.
Thank you.
I hope that answers the question. Thank you.
Thank you, Rihan. One quick question, Rihan. Have you come across any model endeavor where people have tried to couple the gas dynamics of thermal spray together with the solid particle of the powder?
Yes, I can't remember the name of the researcher, but there has been some, I can dig that up, where some research has been done using a CFD kind of type of investigation. And I think it was a team in Canada, if I remember correctly, where you actually incorporate the heat transfer in flight and then try and understand the behavior of the particles. The limitations can sometimes lie in the fact that it doesn't tell you the stress. It can give you the thermal kinetic behavior, but not always the residual stress, which we are actually interested in finding out. So Eulerian technique, which I mentioned earlier on, is actually an offshoot from a CFD modeling technique, because in CFD your mesh is fixed. So that has actually come on board somehow, but there are still limitations of some of the commercial softwares. And perhaps as we move forward, at the moment we have to write, for example, in Python script in Abacus or some other, to actually incorporate these kind of interactions which we want the model to consider. But maybe once they become more like a graphical user interface, then it becomes a lot more easy to adopt these kind of changes. And so I think one of the things which is missing, and I think I probably forgot to mention, I think even in molecular dynamics, the main thing which is missing is probably the graphical user interface, whereby 30 years ago when we started the finite element modeling, everything was Unix, and you have to type, draw a line between these two coordinates and sweep the line to make the mesh. And now the reason it's so versatile and applied to so many industries is because of the graphical user interface. You can just see physically and just do it. And I think that probably will be the trick to when we go towards multi-scale modeling. And I'm not saying that there are not softwares already out there. There are softwares out there which can probably do some of it, but not at a level where we want them to be.
Sure. One more, maybe kind of a comment, Rihan, maybe partly addressing Gustavo's query, which we probably can flag up to here, is one of the great limitations in this area has been on material constitutive models, which have not been particularly good to predict the heterogeneity of the materials that we produce often through coating material. So, I mean, you said about the behavior that we usually model is a continuum behavior. And the previous talk of Chris already showed the kind of microstructure variation that we get through thermal spray and other coating processes, which are often very difficult to be accounted for in developing the material constituent model, even with the MD simulation and so on. So you will have to go to that kind of a discrete approaches where you have to do metrics and then microstructural thing, hard particles and so on, which I think becomes a very tedious task for any modeler, which you will acknowledge, I think, surely.
Absolutely. I think one of my students probably in the talk now, he would probably be saying that that work which I showed for the tungsten carbide particle towards the end of my presentation, where we could embed the particles. And actually there was a recent paper which came out, I think from one of the editors of the Journal of Thermal Spray Technology, which is also looking at. So what we're actually trying to do is basically have a schematic of the microstructure and use some sort of nano indentation technique to find the mechanical properties of each phase in that material. And then we use that SEM as the mesh generator. And this can be actually done in finite element method. And once we have the mesh, the correct mesh with all the phases, including porosity, hard particles, soft particles, and some sort of interaction definition between the matrix and the carbides, we can actually then subject that sort of coating material to either mechanical or thermal or a combination of the two loading. So that's actually, there is research already going on. And I think the example of tungsten carbide particles within the matrix is just the beginning of this process. Ideally, we just want to take the SEM like the one Chris showed and basically just use it to develop the mesh and extract the mechanical properties using nano or some other techniques. And that's actually doable in the near future.
Okay. All right. So yeah, that was brilliant, Rihan. I think there are no more questions. People are already thanking greatly for your wonderful talk and various wide examples acknowledging your team, including I see Fardan and Professor Fazal.
Yes.
Yes. Really to see that kind of a teamwork. Amazing. So I'd like to thank you, Rihan, once again for your wonderful talk and the valuable time that you have shared with us. And yeah, look forward to interacting and collaborating with you.
Thank you, Saurav, and really appreciate all the team at the DSM network, and look forward to the next talk.
Yeah. Thank you, Rihan.
Thank you. Thank you. Bye.
Okay, so after that modeling effort, let's switch gear to Professor Harpreet, who is going to share history and evolution of cold spraying, which is another phenomenal technique emerging very, very rapidly at the moment in the area of spraying. So, Professor Harpreet, can you hear me?
Yes, sort of, yes. Yeah.
Great.
I'm ready to go. Yeah.
Okay, fine. Yeah, great. So perhaps before I begin, maybe I should say, while I was introducing yesterday Professor Sanjay Sampath as being one of the best export of India in thermal spray, in that same category, if I have to hold you, then I would say you are probably one of the best inward talent that has retained in India for the benefit of the vision that India is having for developing as a 5 trillion economy as a nation, which is a great effort to see. And you have very nicely developed one of the unique thermal spray facility at IIT Ropar, which is where Professor Harpreet comes from. So those who are listening in, they are very much encouraged, and probably I'm sure Professor Harpreet would nicely welcome to show you the facilities that are developed at Ropar. So Professor Harpreet basically is a professor at IIT Ropar in India in the Department of Mechanical Engineering. And after pursuing his bachelor's and master's, he went on to do his doctorate degree from IIT Roorkee in 2005. During his PhD, he was working on high temperature corrosion of superalloys and its prevention by plasma spray. And since then, he has been doing extensive research in several areas related to surface engineering and manufacturing, and has authored already several book chapters and contributed more than 175 research papers in various reputed journals. He has completed and been pursuing several national and international sponsored projects and international industrial consultancy assignments. He has 2 Indian and 1 US patent to his credit. He is recipient of Kansai Narrow Excellence Award for the Excellence in Coating Research, a Young Scientist Award, a Career Award for Young Teachers, a Maharashtra State National Award for the research work done by the teachers of engineering, by Society for Surface Protective Coatings and Punjab Academy of Science, AICTE, to name a few. He's currently also maintaining an adjunct professorship at Swinburne with Professor Chris Burnt. And through this talk, we look forward to hear about the evolution and developments that are advancing in the area of cold spray. So without further ado, Professor, I greatly welcome you to the DSM network and look forward to your talk.
Thank you very much, Saurabh, for this introduction. Let me share my screen. Can you see my screen? Can you confirm?
Yes, we can see.
Okay, so my screen is visible and my voice is clear, right? Thank you very much, first of all, Saurabh, for this introduction, and of course the opportunity to interact with the DSM network. And of course, I can see a lot of young people over there, and some of the very prominent persons, expertise all across the globe. And it's indeed my pleasure to be here and share whatever knowledge we have or experience we have with cold spray. So the title of my talk will be Perspectives on Cold Spray. So I just want to introduce it and some of my comments on how it's evolving and what it has in future for us. Before I start, I will just introduce my institute. It's Indian Institute of Technology, what we call it. And it's a very young institute. It was established in 2008. So we are only 14 years old institute. And we have several departments now, 11 and 3 centers. We have a faculty strength of over 175. And we run, UG courses also. And that's what for IITs are known for. It's over 1,000 students we have. Then PG students and PhD students, we have a significant number. In fact, we are aiming at 50-50 ratio of UG and PG students. We have been highlighted in world ranking as well, especially this D ranking, what we call. So we have been kept in the bracket of 351 to 400 slab at a global level. And we are placed very well in Asia university ranking as well. Now this is a little bit about our group. We call this group as a Your Lab group. And here we have been working on two aspects. One on surface engineering, another is on additive manufacturing. Now, this surface engineering is something which we started right from my PhD days ever since 2002. And we have been, developing, just a minute. Well, I think that possibility is not there. Anyway, so I will use this cursor. So we actually, our work is more towards applied kind of, applications of your thermal spray field. And we have started, working with industry because we were not having these facilities like high velocity oxy-fuel and plasma spray in-house. Rather, we have been working with some of the industries in India to develop coatings and then evaluate their performance, characterize them, and so on. So one of the performance areas where we have worked is high temperature corrosion oxidation and erosion corrosion resistant coatings for boilers, where we have developed some coatings through plasma spray, HBF spraying, and D-gun as well as cold spray. So I can say that we evolved as thermal spray techniques also evolved. So simultaneously we kept on taking those technologies somehow, and we kept on improving the performance of boiler coatings in one way or the other. And we have also worked on hydro turbines applications because we are situated near this Himachal zone where we have a lot of hydropower stations, and we were sensitized to this problem of slurry erosion and cavitation, and that's where we have developed some coatings in that sense as well. And so is the case with biomedical coatings also. So we have done some work on these biomedical coatings through this high velocity flame spraying as well as cold spraying. This is the recent which we are doing now. Avnish is going to share this work day after tomorrow in this very workshop. And another aspect which we have just started exploring is additive manufacturing, because cold spray, of course, through cold spray, not through the conventional routes like SLM or SLS, etc. That is where we are taking some lead in the sense of proof of concept kind of samples and so on. I will not spend time on this. This was like just to those who don't know about thermal spray, but now we have some of the excellent lectures already in this workshop. So thermal spray process, we know that we can deposit these particulates by melting them, or sometimes in semi-molten states, and we can propel them towards the substrates to build coatings in laminar fashion. Different types of technologies are available as we progress through this ladder of thermal spray. In fact, this is a nice representation of evolution of thermal spray technologies by Davis, and you can say ever since this Dr. Scoop has come up with this idea of thermal spray, which he got inspired when he saw his son playing with shorts. That's where quite often I tell my students that see the power of observation. So he could see his son playing with shorts with racket, and then he thought, why not to propel the molten or semi-molten particles towards the substrate and see whether they are sticking and so on. That was the start of story, a very nice observation, and which then went on. So many coating techniques they came up, plasma, D-gun, and high velocity oxy-fuel, and then in again 1980s, this peptin cold spray process came up. It was again outcome of an excellent observation during those wind tunnel experiments and so on. So we can have this cold spray. Then CGT took it up and they developed some very nice systems for us to use, and similarly then plasma beacon came and so on. So in that, it's not only about the technologies, but rather there was a lot of another development in terms of diagnosing this process, controlling this process, monitoring this process, and so on. This is again a very nice schematic which can tell us about the two aspects of our thermal spray. We usually call them TV process, that means temperature and velocity processes. So we use temperature and we use the velocity, right? So based on that, we can nicely characterize or differentiate, actually categorize our different thermal spray processes. So for example, this is flame spray here. So temperature is on this range, whereas the particle velocity is less here. So this whole, I used to tell my students, this whole story is based on TV, and we kept on decreasing T and increasing the V, because as an engineers, we don't like temperature that much actually most of the time, because it consumes money, right? And of course, it offers a lot of other challenges in terms of equipment. So we kept on, reducing this. If you see, the whole thing goes like this: temperature is getting down, but then velocity is getting increased, and we are getting the benefits of high quality coatings, even with velocity, right? So we are at a stage when cold spray uses almost solid state particles and so on. And we got some very good advantages as well in terms of quality of coatings, like reduced porosity and so on, and cohesion, which is one of the challenges between different laminae and so on. And we could, decrease this material oxidation and other challenges as we could decrease the temperature. So probably that's one of the reasons why cold spray has been, considered by so many people. But there are challenges we will understand as we progress through this this one. Here are a few of more, specific, data about it, but I am not going to go in detail. But one thing which we should keep in mind, that in cold spray we are in a region where we are now working on supersonic velocities, like we are working in Mach number of 2, 3 and so on. So in fact, we can in HBF as well. So we are in supersonic regime of our velocities. Now, why we are talking about this thermal spray market? Of course, Professor Sanjay Sampath has told us a lot. Actually, this is a small kind of information in that comparison, I would say. But if you see the global thermal market share, this is the scenario here. The plasma spray is basically dominating this market till 2019. This is 32% share is taken by this one, and which is then followed by this flame spray, given its simplicity and so on. And then HBF has picked up very nicely, and this is arc, and cold spray is a lot to go, but still it has reached to double figures and so on. Now, if in terms of outlay, we can see that this global thermal spray market is picking up, in terms of billions, and we are projecting that by 2028 this will be $14 billion market, right, with the CAGR rate of 4% and so on. Of course, this is much less when we compare with additive manufacturing technologies. Anyway, so dominated by plasma spray, as we have seen. Now, since we are talking today more about cold spray, so you can see that the global cold spray market is of the order of 956 millions, which is to be increased to 1.2 billion by 2027. So these are all projections. We don't know exactly or what is going to happen, but still this gives us some kind of hope that cold spray is going to pick up in the times to come. And you will see even through as we progress through our this presentation that the adoption of cold spray is mainly in aerospace and automobile repair, and it's also growing in terms of maintenance, manufacturing technologies. So high pressure. Now, when we talk about cold spray, there are different variants of cold spray. Even so, we have low pressure cold spray, we have high pressure cold spray. So among that, high pressure cold spray is contributing majorly to the tune of 57%. This is like share, sector-wise share of cold spray market. Now here you see 46% goes to transportation, which is again aerospace and automotive. Mainly then utility, where we talk about these boilers and other utility equipment, turbines and so on. Then we have electronics market and so on. Yes. Medical share is also of the order of 4%, which is kind of increasing, especially when we say we can do additive manufacturing of standalone, your freestanding implants in future. This is again a very basic information about cold spray. Now, when we say cold spray, as I said, temperature is brought to very minimal, but the main driving force to adhere our particles is the velocity here. So that means we have to have something to accelerate our particles to supersonic velocities, and that is where we use this D-level nozzle, which is divergent nozzle. And this is kind of heart of this whole cold spray system. A lot of studies, a lot of design attempts have been done on this nozzle so that we can achieve these supersonic velocities required for this. So this nozzle is fed with the our gas, working gas, which is usually nitrogen or helium or sometimes air as well. And that air or that gas is basically accelerated through this nozzle to supersonic velocities. And in the meantime, we also introduce our powder so that it gets accelerated through momentum transfer from the gas to the particles, and particles can achieve the desired velocities to get deposited on the surface. How they are getting deposited, I'll give you some hint, although my previous speaker has already talked about it slightly. So there are different types of adhesive mechanisms which are working here. And another thing is that we also have heater here. So sometimes some Some people ask why then we are heating it. So this heating is mainly for thermodynamic reasons, I would say, because we have this expansion at the throat. That means we will have this adiabatic expansion of our gas, which can lower down the temperature of the gas, and it can hamper the critical velocity to be achieved through this one, right, or velocity of the gas. So that is why we heat the gas here. We have the capabilities of up to 1000 degrees Celsius as well. But the major reason of heating here is not to heat the particles, but to heat the gas, actually. And of course, some heat is picked up by the particles, but that is not the prime objective of this. Okay. Of course, this facilitates to some extent. They soften some particles, but the majorly it goes for the this thermodynamics reasons here. Again, a lot of studies, a lot of simulation guys have worked on, designing these nozzles and so on. If you see the literature. Now, what are the major process parameters in cold spray? So we have, as we know, as the particle will impact on the surface. So two things are important. One is particle velocity, another is particle temperature. So particle velocity, is then these are the parameters of cold spray which will affect our particle velocity. For example, stagnation temperature, pressure, process temperature. As I said, pressure, this temperature will facilitate to achieve us higher velocities, nozzle dimensions, type of carrier gas, and so on. Helium is quite interesting, quite a lighter gas, can give us very nice critical velocities or velocities required, but again, it comes at a price, so we have to have some other options and so on. So and of course we this particle velocity depends on particle size as well, density of the material, and morphology of the feedstock and so on. So and particle temperature will definitely depend upon the carrier gas and process temperature, nozzle material, nozzle dimensions, and specific heat of the feedstock material. So among these, some of these are system parameters, these red ones, and then we have feedstock material parameters as well. There are some other very important parameters which we should not skip here. One is the scan speed. It's like how you what is the travel speed of your gun over the substrate or relative to the substrate, and standoff distance, and then spray angle. So all these parameters, they play a significant role in dictating the properties of your deposits. This is a little bit on bonding mechanisms and window of deposition. See, although this bonding mechanism is still like a lot of debate in the literature. If you see into the literature of cold spray bonding mechanisms, there are like a lot of studies going on it through simulations and so on. So I mean, we are not at same page, at least all the scientists across the globe, but there are now certain kind of clarities coming up with the time. One thing is that critical conditions for bonding occur at the interface region due to extensive plastic deformation. So one can expect that when the particles are coming with very high kinetic velocity, so they are going to stop all of a sudden within a very small standoff distance. So you can see that there will be extensive plastic deformation, or what we call severe plastic deformation will take place within less than second, or in microseconds and so on. So that we have much localized heating near particle substrate interface. So if you see here, and usually this jet type of flow occurs at the interface. It is being modeled by several people now. That how this particle comes and then how it is getting this sticking on the surface. So when the particles undergo deformation at much higher velocities, So basically, when the particle will come, it will strike on the surface, and there will be a kind of heating, localized heating along the interface, and that heating will dominate, or it will result into softening of this particle. Why we are talking about hardening here? Because another aspect which is coming or competing, it will be the hardening, right? Strain hardening, because you are impinging something on the surface, and as both these surfaces, particle as well as the substrate, they are plastically deforming. So one can expect strain hardening as well. But then this temperature also plays very critical role, and this softening basically dominates, and that's why this particle will tend to deform like in this particular fashion, where we get this kind of flow of the material, plastic flow of the material, which we call jetting. This SRD has shown it very nicely through molding as well as through some of these this one. So these melted, melted regions you can call, they help in forming the substrate and particle interaction. Now, one of the as we go through this, we can now understand that one of the requirement for our feedstock particle is that it should be ductile, because we are talking about plastic deformation, right? If your particle material is brittle, then we can expect that we will not be getting very nice coating. So that is one comment from this side. Another thing is this is again a very nice schematic, which shows us the material deposition what you call deposition efficiency of our cold spray. Which means that suppose if you are depositing, say, or pushing 1 kg of powder towards the substrate, how much it's going to be stuck on the surface, and that ratio will give you the deposition efficiency here. Now that deposition will or in fact this whole coating formulation depends on the velocity of the particles, because velocity will dictate how much energy we are going with, which will help us to deform on the surface. Now there we have seen that for each set of material, that means feedstock material and the substrate, we have some critical value of velocity at which the particle will start sticking on the surface. It's not that you will propel them and towards the substrate and they will stick. So there has to be some threshold value beyond, or which will start, or which will help you to retain the particles on the substrate, right? So for example, in here, this is the point. And then, of course, then you can increase the velocity, okay, to increase your deposition efficiency. And then there will be again upper limit on this, beyond which again you will see that the particles will start, eroding the surface rather than sticking on the surface. So here they are rebonding, but here they are sticking on the surface. So that is something. So that means our useful process window, or window of deposition as they call it, it is limited by our this velocity, and that is the actually our job. Whenever you get new set of material, feedstock material and the substrate material, and the first thing is to see what could be the critical velocity, and that is the whole challenge actually in cold spray. If it's a new set of material, sometimes you will have not many options, but one is that you experimentally determine it, but then it leads to a lot of cost, and then preferable approach is the simulation, or by some mathematical modeling, we need to calculate those critical velocities, and that is where a lot of opportunity lies. Of course, there's work have been done, but still there is scope for that simulation. Another critical question is that why cold spray coatings? Because already we have a lot of prevailing thermal spray technologies already well established, for example, plasma and HBF and so on. What is so special upon these cold spray coatings? The one thing is that this is a velocity driven process, right? So temperature is very less. In fact, there's no melting of the powder. It is heated in the process, but not well beyond its recrystallization point. It's like just warming the particles and so on. So that means oxide formation will not be there, because in coatings, those who work in coatings, they are always worried about these oxides which can form actually. And this challenge becomes more when we have low melting materials or temperature sensitive materials. So in that domain, cold spray can be a very, very nice technology by which you will get oxide free coatings. Another thing happens is that plastically, again, deforming the feedstock powder, it's like a severe plastic deformation process. And in that, we have seen that this there is a kind of grain refinement also happening. So there are studies where we have seen that there is a dynamic recrystallization during this severe plastical deformation, and you can see the microstructures are quite impressive. And of course, microstructure, if it is refined, you can expect better mechanical properties. Coating thickness. Again, here we have a wide range of coating thicknesses. We can consolidate more and more material in cold spray, given its good adherence and coherence between the different layers, and you can develop very thick coatings. And that's why it is being attracted for repair applications as well. I'll show you some of the case studies. Recycling of powders is again possible here because we are not heating the particles. At least to those temperature, melting temperature or near melting, right? As we do in HPF or other processes. So possibility of recycling is very, very important. And please note, this is very important point from industry point of view, because I remember we have one vendor from the industry who was using very expensive powders. So he can't afford to lose that powder on the shop floor. So this process can help us in that sense, because one may say that the whatever is not deposited can be collected in other processes also. But here, what my point is that whatever is not deposited, it will come back, right, in somewhat nascent form. It will then be collected, and less secondary processing will be needed to again recycle this powder. That's what I meant by this. So what are the advantages? High deposition efficiency, for which industry people are always worried about. High deposition rates, again, we can deposit very, very the coatings with the high deposition rates. Working with dissimilar metals, it's not that big challenge here. Separate thermally sensitive materials and dense as well as porous coatings can be obtained. So we can always, tailor the coating properties, because in certain applications we need some porous coatings, as Professor Burnt was also showing in some of the turbine applications, or in your biomedical applications, we usually need some kind of porous coatings. But then what are the limitations? So coatings are brittle due to extensive plastic deformation. So this is one thing. That means we have to do some kind of post-coating treatment. Another is economically challenging. Quite often I have seen that it's my own analysis, I may be wrong, but I have seen that the cold spray right now is being used for high value products right now. And that is challenge behind in front of all of us, that how we can make it more economical, right? Maybe in terms of recycling of powders and recycling of the gas. In fact, we use high volume of gas in this cold spray, and that worries me a lot, right? So we should have something. Of course, there are efforts to recycle those gases and so on. But still we can ponder upon what can be done in future. Oxide content is generalized CS coating is less than the oxide content. Now, this is interesting observation by one of the papers, that the oxide content in the generated CS coating is less than the oxide content. So probably it is because then even if your powder has some oxide layers inherent, they will break down when they impinge on the surface and so on. Now, in terms of evolution of coatings and feedstock in cold spray, I can comment on that as well. So, if you see the history of cold spray, people started with soft metals and alloys like aluminum and copper and zinc, etc. And then they started exploring these titanium, niobium, titanium, and tungsten, and so on. Then hard metals, a lot of work we will see in titanium alloys. That's why biomedical applications and aerospace. Inconel alloys, it's very again interesting from aerospace applications and so on. BMG, HEA, and so on. And then we have composure coatings. Again, very important contribution by cold spray. This is like metal or metal ceramic coatings. They can be produced even up to 85% of ceramic content can come. So only challenge, as I said, is standalone ceramic. Okay, so that is somewhat challenging, and I put this challenge to our young colleagues over there. Maybe they will explore. Of course, there are some attempts, but still, standalone ceramic, or I will say brittle materials, is still a big challenge. Then, what are the current trends? Metallization of polymers or metal polymer composite coatings. These are all have to be explored, because this can help us in several other applications. So we can, for example, print some electric circuits on some of these polymer sheets or other way, right? And so on. So of course, things are moving ahead. A lot of new applications are being explored, and so on, right? And in terms of feedstock, we have this atomized feedstocks being deposited, having splat boundary, of course, up to this nice coating standalone powders, maybe metals alloys. But then we have this, in case of hard phase, we have these in core shell kind of powders where we have soft binder on it, and then we can deposit them. But then there's a lot of this composure coatings work also, where we have softer binder and these reinforced particles, which can be then mechanically mixed and then can be deposited and so on. And there's another soft phase and hard phase kind of fused kind of what they call fused and sintered, and then when they are deposited, they can get disintegrate and so on. So as I said, another aspect which we should not forget about cold spray coatings is the post processing, because usually they become very brittle due to that sphere plastic deformation. So what are the benefits here? It can reduce porosity, it can improve inter-supplat bonding, and it can improve properties like electrical conductivity, elastic modulus, flexure strain, and so on, and decrease the strain hardening, therefore decreases the hardness. We could all imagine, I have seen in most of the applications, you have to go with some kind of, these treatments. And there are a lot of, development in this domain in terms of creating technologies for post-processing of cold spray coatings. For example, vacuum heat treatment is traditional, but then we have post-deposition short peening, as we do in other components as well. Laser-assisted CS is another technology, hybrid technology, which has been utilized for in situ kind of helping to mitigate the effect of this brittleness. And in situ hammering is another concept where we have these solid particles, hard particles, which simultaneously do this hammering of this one. In one sense, we are doing this peening effect as well as coating simultaneously. And of course, we can use laser remelting of coatings as well. But each of these processes will have its own advantages and disadvantages, and we have to select accordingly wherever we wish to go about it. Now, this is some work which we have done. I just wanted to show, especially on cold spray coatings. So we have done this work, in fact, in 2009. in collaboration with EASP Industries USA. So at that time, we were working on this nickel chromium coatings, nickel 20 chromium coatings, and we wanted to enhance the performance of these coatings, because these coatings we were designing for this boiler applications, where there's a lot of erosion also taking place due to this hard part, fly ash particles and so on. So there we wanted to enhance the properties of this nickel chromium, and there we use some titanium carbide kind of reinforcements. And also we wanted to see the effect of rare earth elements, and depending on the availability we could find this rhenium, basically to peg the layers. Actually we know that these these small fractions of these rhenium, these rare earth elements in our materials can help us to peg the layers of oxide layers. It's well established, for example EGI and others. So we also wanted to try that in this combination. So we developed these coatings, and we could see that, and we tested them in oxidation as well as erosion corrosion and hot corrosion. In erosion corrosion is we tested them in the actual boilers. Actually, we had some collaboration with some of the local thermal power plants. We hang those samples in some of the recent superheater, what they call lower superheater zone, temperature of the order of 700 degrees Celsius and so on, and we measured the thickness losses and so on. So these coatings were very intact. Actually, they reduce our rates in almost all environments, and you can see this coating even after exposure for 1500 hours under cyclic conditions. Nothing happened to this coating much actually. So that was kind of interesting for us and encouraging for us. Of course, we continue that work. We then wanted to develop nanostructure coatings. In fact, one of my colleagues, he was extracting this nickel and chromium from some of the waste plant, these pickling plants in nearby industrial valley town. So our dream was that if we can extract those nanoparticles of nickel and chromium from that sludge and then form them as a coating. But of course, we could avail some powders, but and we developed some nano particles through our chemical routes as well. But when we but the challenge which we faced was our powder feeder did not support us during cold spray or even HVF spray. So flowability problem was big at that point. This was pretty 2014 or so. So then what we did, we actually used those nanoparticles in our micron size particles, and we made some mixtures out of it and allied them, and we tested them, and because these powders are milled, and so we could have some kind of nanostructures in our coatings, and those coatings were tested, and we benchmarked them against our normal nickel chromium coatings, micron size, and then these blended ones, and we could see that we could enhance the properties of these cold spray coatings through these addition of these nanoparticles in certain fractions in the micron size. So this is the comparison here, right? So this is our conventional coating. This we called nanostructure, and so we could see that erosion, corrosion, oxidation, it was reduced. And moreover, we also established that this cold spray is slightly better than HBF spray, at least for this combination and so on. This is another work which I would like to share with the audience. This is again, we did some work on, in fact, we were developing this very thick coatings for some application. This was some project by Government of India. So our aim was to develop 3 mm thick coatings, pure copper coatings on steel for some passivation in some reactors and so on. So their objective was one, of course, was pure coatings. We wanted to have high thermal conductivity, high electrical conductivity, and a very good adherence with the steel. So in that whole project, one of our student Surinder, he did this wonderful work. The challenge was the major challenge which we are facing was in terms of adhesion. So there we study or we investigated the role of the surface roughness of the substrate on the adherence of our coatings, right? And there he used these different conditions of substrate in terms of surface roughness. So we have this mirror finish as well as semi-polished or and as received. These are some of the roughness values here in terms of RA. So then we deposited these powders and we could see that our mirror polished samples, they were giving us very nice adherence. In fact, let me tell you that this is again a point of quite discussion in the literature. If you see, some studies show that rougher surfaces are better for good adherence. Some others are saying it's like polished samples and so on. But when we investigated, of course, we were more towards Hassan's group's argument that mirror polishing is giving good adherence. So we did this study with single particle impact as well. So my student worked a lot of details on it, that why there was good adherence. In fact, we established that there was no hindrance to this particle which is coming here from the peaks on the surface, whereas we could see the peaks on the semi-polished surfaces, which could absorb a lot of energy of this particle to deform, right? So these sharper peaks, they deform, and then that is why energy is dissipated of the particle, and there is always kind of gap between this between the coating and this one, right? But here you can see the particle, the whole energy of the particle is getting used to get the adherence on the surface and so on. He established this with the help of Astm. He did a lot of Astm analysis and so on that. Saurabh, please inform me about the time. Sometimes I lose track of time.
No, it's fine.
So
it's
you can
totally okay. Yeah, please go on.
Yeah, you can always warn me 5 minutes.
No, we have about 15-20 minutes.
Yeah. So this is the same same coating, the copper coating work, and here the objective was to increase the this electrical conductivity, because we were given this target by the firm. So, and that's where I want to say that this post coating heat treatment, that this heat treatment of this coating helped us a lot. This was we did its heat treatment, and we could achieve that target easily. Now this is our another set of work which Nish is currently doing. This is about Professor Christopher Walt has already shown you some coatings through plasma spray of this Baghdad, which is now getting kind of attention, being a possible replacement for your HAP, because it shows some very promising biocompatibility and other things. So what we have done with cold spray, we have tried to develop these coatings in-house here, and some success has been achieved in that, in terms of having a high corrosion, or you can say reduce the corrosion of the substrate material, and of course wear loss. And of course we have tested these coatings for cell culture studies have already been conducted, and these are quite biocompatible and so on. Now this is another, I was telling you, metallization of polymers. There's a lot of interest actually for solar applications and electrical applications and so on. So people are trying to deposit metals on polymers, right? So this is some work from the literature where people have done these coatings on different types of polymers, and even these composites, GRP, GR, and glass fiber composite. Sorry. And this copper, and some innovations have been done with regard to improving the adherence of these coatings with the addition of certain, other elements like tin and so on. Okay, and see, with very less temperature and pressure of cold spray, they could develop these coatings. Why I'm always talking about cold this pressure? Because those who run these cold spray systems, they know that it means we can save some gas, right? So it is always exciting to reduce this value, right? And this is something which we also gave try at IIT Ropar, where we developed this copper ring on this polymer sheet, this PMMA sheet, and things like that. Now, I switch my gear to one more aspect of cold spray, which is kind of attracting attention. That is about additive manufacturing application. Now, why there's interest? Because it offers some kind of advantages when you compare it with our conventional, say, selective laser sintering or selective laser melting processes. One obvious is the low process temperature, so thermal stresses are absent. In fact, we have some compressive stresses which are even better. Sphere plastic formation and low temperature, we have more refined homogeneous microstructures, low oxide. And this is important, that reflectance. So here we are not bothered even about materials thermal conductivity or reflectance, because in laser-based systems, high thermal conductivity poses a problem because localized heating becomes a challenge and so on. And of course, we all know that when we have a laser, the reflecting materials can pose some other problems. Of course, there are remedies to this, but cold spray, we need not to do anything with the reflective materials. As it is, we can do that. Okay. Another thing is this multi-component materials deposition. This also does not pose much problem in our cold spray, whereas in SLM and SS, where we have multiple materials, multiple component materials. For example, you are having 2-3 materials, so they will have their own thermal properties, and while you will be sintering them or melting them, they will pose their own problems and so on. Okay, less distortions are expected, and of course, in some way, it is more eco-friendly as well. But when where we lack here, this is positive point about our cold spray, that we can have very high deposition rates. But in terms of shaping fidelity, of course, we are limited because maneuvering your robot in 3 or space is somewhat difficult to get some intricate or difficult geometries, right? There is some attempt by this one group, Pattison. They have done some modification on cold spray system, to make it just like a machine tool. And they are manipulating this cold spray gun through our CNC, program and so on. Yeah, I mean, there are a lot of scope to do that. Here are some of the applications. I'll just glance through that. You can see that people have developed already some kind of freestanding, biomaterial, these kind of components, and you can see this lining here, and this is brass flange copper, not this copper flange anyway. So this is also 50 to 60 mm thick deposition has been done here, and this is a repair application. Again, a lot of people, a lot of industries approaching us that can we use cold spray to help them out, right? I mean, sometimes very unexpected kind of vendors are coming. Unfortunately, I can't disclose those, but it offers a lot of opportunities for us to for these repair applications, because these, especially high value components, okay, that you have to still keep in mind till we get some very cheaper version of cold spray. Operating costs in terms. This is, I think, Christopher also showed these kind of things. These all aerospace applications, and this is interesting. This is gear being made, and with cold spray. this all repair and other applications. This is joining, people are filling these cavities and then finishing it, and sometimes they are using filling the materials and then doing some other secondary processing like friction stir processing or something like that. Electrical appliances, again, they are approaching. In fact, we are also also developing some product for a well-known company through cold spray, right? So these all applications, interesting applications are emerging. This is again, I can't disclose much details on this because this is something which we are doing with some industry. So idea here is to develop two standalone geometries, and we are trying. This is the first phase of work where we established the capabilities of our system to develop these very thick layers of titanium and nickel to anti-chromium and so on. We tried certain, post-coating treatments also to enhance their properties and so on. So this work is we are carrying out, and now we are in a phase to develop that component, freestanding component. Now this is the last phase of my presentation. Of course, I'm not an expert of this. Again, disclaimer from my side. But cold spray process, as I said, it's costly to run. You can't keep on doing hits, lot of experiments to arrive at the desired process parameters, or in other words, designing the process for a given application based on experimental will make no sense actually. So that is where people have, in fact, this process is happening so fast, even certain measurements are very difficult to take simultaneously as well. So what to understand, how to understand them, that is the second challenge. So that is where a lot of people are doing simulation work on cold spray board, and especially the younger generations. So similarly, our group also, some of the newcomers, they have started thinking about simulations, although my main work was in applied kind of application part. But if you see this interest, yearly publications on these FEM models, it is in this fashion increasing, and the citations are also increasing day by day. And what they are doing, or what they are simulating, so they are trying to simulate the bonding mechanisms, nozzle geometries and its optimization, and clogging behavior, which is one of the challenges. Other aspects, residual stresses, properties, some of things we have already seen from our previous speaker, Dr. Ahmed, in situ hammering, and all these processes people want to simulate, and there is some kind of success, some level of success already been there. In fact, simulations, they have helped us a lot in terms of understanding the bonding mechanisms. Even Dr. Ahmed talked about this adiabatic shear instabilities, hydrodynamic plasticity, localized melting, and mechanical interlocking. These are all kind of different possibilities of bonding mechanisms. And this is one interesting study by SID where he's simulating this particle, and he's monitoring these two nodes. This is a particle which is coming towards the substrate in the cold spray process, and he's monitoring these nodes and with certain these parameters. See the time scales here, nanoseconds. And there he has seen that he has monitored the strain and stress, 3 parameters through simulations, and he could see this rise there. And that's what we were talking about, that there's certain increase in the temperature and strain at the interface, okay, and drop of stress. In fact, that gave us the idea of this, what we call adiabatic shear instability, that the material loses its shear strength all of a sudden, and it flows, in the form of the jet. But then there is another, thought process where this hydrodynamic plasticity effects are emphasized, where we say this pressure wave basically helps us to adhere, and then is localized melting. But I would say that we have to correlate these mechanisms with the nature of the feedstock powder and the substrate in terms of if material to be deposited hard and soft the substrate, or soft on soft, or hard on hard, or hard on soft, or soft on hard, and so on. So that will also be helpful to identify one of these. Okay. And of course, oxide layer breakup is something which always takes place if you have that. This is some simulation work. I said some of the new entrants in our lab. Under the, we have a faculty also, Dr. Manish Agarwal, who is now taking interest in these simulations. So some of the simulations or published work we have already done 2 publications on that. One was a study on dependency of critical velocity on material properties. So where we saw that yield strengths, stain hardening exponent, and strength coefficient are predominant factors influencing the critical velocity. In the second study, we have seen the effect of particle size. Of Dr. Manish Agarwal, I would say, under his leadership in our lab. So because he has some affinity or expertise in this machine learning, so he is involving some of our students in that machine learning aspect as well. So because of course people are using a lot of FEM simulations, but they are computationally intensive. So what is the way out, right? So that is where this machine learning is one of the possibilities which we are trying. Of course, a lot of people are trying in this area as well. Okay, because you can't always do head and trial experiments, as I said, and of course, empirical relationships kind of approach is also being used, but again, those are having limited accuracy and so on. So of course, FEM simulations have worked us a lot, but then the problem with that is that they are computationally intensive. That is where it was thought that machine learning approaches can be useful. Okay. In fact, this is from literature. So some efforts already are being there where this machine learning techniques and regression models have been used to predict the deposition efficiency. So they have taken this kinetic energy and thermal energy of particle as the input, and then they have used different techniques and to predict the deposition efficiency. Of course, there is a limit on accuracy. So, but what we have seen there, if you have to take some lesson from that study, is that we need to have some more input parameters and data sets to improve this prediction efficiency. And maybe neural network technologies should be used, because thermal spray, this cold spray process is highly non-linear, so that has to be kept in mind. Similarly, there's another study by Wong where they have done this, use this machine learning aspects to predict the critical velocity in the process. This is the framework used by them, so they have used some of these technologies to predict this, and their predictions are quite nice actually. They have used this neural network approach, which showed better results. Okay, and they have also included some material properties into their model. So our approach, what we have, I'll take 3-4 minutes more now. So what we have done here is we have seen that deposition efficiency, hardness, or these are some of the parameter characteristics. If we can find that can be useful for our cold spray coatings. So how these 4-5 parameters, they can be easily, calculated or estimated if we know these what they call PQ, which is basically current plastic strain and temperature of splats and bond masses stress. These 3 parameters, if we can predict, we can then arrive at this with the help of literature. Now here, one approach is of course simulation, right? But then there can be another approach, which is our machine learning. So that is where we have tried something here. But then the point is, what is the framework here? The framework which we have used here is the, we first of all we did multiple coating impact simulations using Abacus we have used, and from there we have generated some data. So we have generated database from simulation for different materials with different combinations, and then we have tried exploring machine learning techniques. So we have trained this machine learning algorithm with the database obtained from simulations to predict the simulation outputs. So that is the approach which we have used in our case. So whatever data we have that from this one simulations, we have used 75% of that data for training our model and 20% of that data for predicting the output. So that is where 2 approaches have been still we have tried. One is simple regression, which we all know. One is one protocol is deep learning model, which has been more helpful for us, and it's more accurate because we can see the predicted values of our PQ. So this is for trained data, this is for test data. So we could see a good correlation between predicted data and the actual data. So actual data, we are talking about the simulation data, and this is the prediction, and this is the testing. So in both cases, typically we say it should be at 45 degrees. So this we have got better here. Similarly for temperature as well. So this is our trained data. So this is good correlation, but it is further improved when we use this deep learning model in this concept. So this is quite a primitive work, I would say, but we are trying to improve these models by having some more input parameters into our model, which may be based on some kind of fundamental equations from our applied mechanics and so on. Now, so this is again one kind of I would say ambition when we talk about digitalization of our cold spray system or in general thermal spray technologies. So we need to see this whole system in the context of Industry 4.0 frameworks, right? So we have made this. This Boo has kind of given some idea about this, so which I liked a lot. So basically, we in a typical cold spray system, we may have different types of modules. One is like spray module here. We have a robot module here, and we have in situ measurement module here, and of course in between we may have this inter-process module, and then we have post-process module. The dream is that we can integrate this as a closed loop, and that is where we need to work in terms of developing more and more sensors so that we can sense the properties of our coatings in situ. It should not be happening that we have the coating and then we test it and we found that it's not good, and again. So why not we have a lot of sensors to monitor it, right, and make it closed loop in the sense that if we are getting some deviation, so we should be able to guide our system to play with the process parameters and so on. So that means making it more and more autonomous by applying our ML and AI kind of protocols on this. And of course, one may further go to connect this whole thing through the cyber systems. So and so on. I think that is where we must be leading to in the time to come in terms of having Industry 4.0 compatible cold spray systems in the time to come. But a lot of things have to be put in place. So I end my talk here. This is the facility which we have at IIT Ropar. This is our cold spray system, which is from Plasma Beacon. It can go up to 50 bar pressure and 1000 degrees Celsius temperature. And we have used it for several coatings and of course for additive manufacturing applications. So I invite people to have if they want to use this facility, we are very much open to extend this facility in one way or other, whatever it looks like. Thank you very much for this opportunity. Thank you, Saurabh. Thank you, everyone, for patient listening.
Thank you so much, Professor Harpreet. Particularly thanks to you for taking us through the evolutionary journey of cold spray, right from the beginning of the motivation of why do we do cold spray to all the way to doing machine learning and Industry 4.0 upbringing in cold spray area. I wish I could hear that more. But I have a couple of questions, Professor Harpreet. So your talk ended on that thank you slide on a sustainable way spraying. So maybe I should begin by asking, can we just use unused ceramic powder to cold spray again, which has been rebounded?
Yeah, actually ceramic powders will face us the problem in terms of, when they will impinge on the surface, they will, get fractured, right? So sometimes they go just like a dust actually. So that is one of the challenges. Okay, maybe you can collect those dust actually, but then how to come back? Maybe they will not even flow through there again for the process. So that is the challenge in ceramic powders. Otherwise, in terms of metallurgy, I don't see much will happen to them, but they will go into fragments, and sometimes they call it ceramic dust. So challenge may be there to collect it. Yeah.
I see. Maybe a follow-on question in some sense that as we all acknowledge that cold spray is a high strain rate process. What are the tools available to monitor the strain rate during this?
Well, I don't have an idea because at this scale, so when things are happening in nanoseconds, in fact, it is difficult. That's where, I mean, people are simulating it here and there. I'm sorry, I will not be able to comment on this right now. But it's a good question.
Well, actually, there are interrelated questions. Like, for example, I was in my own mind, how do we visualize that strain rate, firstly, and be able to assertively do the modeling at that? Because maybe, I don't know, I'm just speculating. People are frequently using this von Mises prediction, but maybe principal stress criterion or Tresca criterion, some other criterion might be befitting more than von Mises. So that prediction might be a bit off from FEA or continuum mechanics. So,
yeah.
But we have done some work in this area. So if you have some experimental data, we would be keen to keep participation in that exercise to look at it.
Sure. Why not? We can have more discussion on that sometime. So, of course,
is gearing towards more of cold spraying areas and other allied thermal spray processing ways. We worked in GE, so we tuned to it.
Sure.
But yeah, an excellent talk. And there's a question coming from Vish, just so when I mentioned him, that he's asking, can we spray silicon carbide using cold spray? What could be the challenges?
Yeah, silicon carbide, again, this is kind of, brittle. I don't see much, it will be difficult to say as it is because due to its brittleness, it will be difficult. But if you allow me to use some binder in it, then it is very much feasible. But again, another question is what kind of substrate we are looking for. If it is softer, Then there are some studies where people are showing that some of these particles can get embedment on the surface, softer. So if we have some softer kind of substrate, then there is a possibility. But if you are again talking about some very hard substrates, then probably it will be a challenge of rebound and so on in manufacturing of this as well.
Great. So maybe one final question, Professor Harpreet, from my side. When you compare cold spray against normal thermal spray, which method would you say is more forgiving in terms of the surface preparation of the substrate?
Okay, so if I understood, suppose we have thermal spray process and cold spray process. Which one is allowing me to have less surface preparation, right, of the substrate? I think in that sense, cold spray is better. I think. So cold spray process can give you, better, because there are a lot of studies which are helping this thing, that surface, even initially, then when the particles they come, they can detach the oxide layers. Maybe in the initial 1 or 2 passes, you may not get the coating, but once they will remove the oxide layer on the surface through this pinning effect of these particles, so you can afford to be having less surface preparation than what you will have in thermal spray processes.
Okay. So once again, thank you so much, Professor Harpreet. I think we have just managed to finish well on time. Actually, we were supposed to finish
Thank you.
in 12:03. So I must thank all 3 speakers who have done excellently keeping the time. And with that, I think we conclude day 2 of this.
Yeah, I think there is a comment by David Hall. So he's saying there's such an aerosol deposition of ceramic particles very active now. Yeah, I think that he's right in that. Anyway, so it's for our information. Thank you. Thank you.
So yeah, that's excellent thought, David. Thank you so much. Yeah, so we conclude day 2 of the thermal spray week, and we have now day 3 coming ahead tomorrow with excellent talks coming from Professor Shrikant Joshi and Professor Armel Bordil. So we are looking forward to tomorrow then. And once again, I would like to thank on behalf of the DSN network all 3 speakers who have contributed significantly for today's talk, starting from Professor Chris, followed by Professor Rihan Ahmed, and then Professor Harpreet Singh. So my sincere congratulations for doing such a groundbreaking work in this area, and I look forward to interact further with you. Also both personally as well as on behalf of DSN as well. So,
thank you.
Thanks very much
Thanks
again.
very much, Saurav and team.
Yeah.
Take care. Bye.
Thank you again. Thank you everyone for listening in. Thanks again.